Greetings, chemistry students. Mr. Presentes again. We're talking about, well, thermodynamics actually, in a term called enthalpy, and we're in chapter 12. So you follow along 386. We're working the problems. We're working the change in energy enthalpy problems on page 386. The definition for enthalpy is the sum of the internal energy of a system plus the product of the pressure of the gas in the system and its volume. You see, it's rather complicated to try to actually determine the absolute value of the energy for every reaction because there's so many variables that are involved. What we do focus on, however, is the change in energy. And the change in energy is what delta H is. Delta just means change. And what we mean by that is the energy final minus the energy initial. And H is the change in energy. And energy, heat is a form of energy. So the units are going to be kilojoules. Alright, so these are going to be the units. The units are kilojoules. And so change in enthalpy is more useful quantity than the absolute value. The change in enthalpy is positive in endothermic reactions and negative in heat-releasing exothermic processes. So here's an example of an exothermic process, and you can see I have the reactants and the products. And instead of just drawing a straight line like we usually do, the line in between indicates that we are along a grid that shows a change in energy. And there's less energy. Where did it go? Well, it left as heat. So reaction Y is an exothermic reaction because the products have less energy than the reactants do, and we lost that energy as heat. And the reaction X, the reactants have less energy than the products, so it absorbed energy. So it would have gotten colder as it absorbed energy from the surroundings versus releasing energy to the surroundings. So endothermic takes energy in, exothermic takes energy out. Endothermic reactions would get colder, like a cold pack that you break and gets cold for instant cooling of sore muscles. Exothermic reaction, well, any combustion reaction would be a good example of that. Okay, so let's show you how to work. Let's see if we can work some of these equations. The we have peroxide just decomposing into water and oxygen, which it will naturally do. How much heat will be released when 5 grams of hydrogen peroxide decomposes? Now, the change in energy, the enthalpy, will be given, and this is a negative 190 kilojoules. You'll have to be given this information because it's unique for every reaction. So we start with the 5 grams that are given, 5.0 grams, and the first thing we have to do is we have to turn those grams into moles, as you would expect. And to do that, we're going to divide by the molar mass, which is 34 grams, and that's to 1 mole. So we have 34 grams to 1 mole, and so how much of a mole do we have? Once we determine that, we're going to multiply by our change in energy number value, and we're going to divide by the number of moles that we have. We happen to have 2 moles, so 2 moles of H2O2. Okay, so this came from this number, this came from this number, this came from this number, and this is its molecular mass, which is, what is it? H equals 1, and O equals 16, but there's 2 of them, right? So, and there's 2 of these, so 2 plus 32 equals 34. So that's where that came from. Okay. Now we just plug this in, and 5 divided by 34 times negative 190 divided by 2 equals 14 kilojoules of heat. Right? Let's try another. When 6.44 grams of sulfur reacts with excess oxygen, how much heat will be released? We'll have to be given this information. Make sure this is a balanced equation. Make sure that there was no errors in the equation, and we're just going to concentrate on the sulfur, aren't we? So it would be 6.44 grams of sulfur, and we're going to turn those into moles by dividing by the molar mass of sulfur, which is, if you look on your periodic table, I believe it's 3207 to 1 mole. Those are grams, by the way, and we're dealing with sulfur. And then we're going to multiply again by negative 791.4 kilojoules, that's a J, to how many moles? 2 moles. So 2 moles. And if we calculate this, what do we get? Bear with me. What do we get? We have negative 79.6 sig figs. We should have used 3 sig figs here. 3 sig figs is fine. Give the joules, and so 79.6. Negative 79.6. Alright, let's try one more. We have 9.22 grams given. So we have to turn this into moles by multiplying by its molar mass. This molar mass is, this is molar mass for glucose. This is glucose, of course, that's oxygen, CO2, and oxygen, so we're dealing with the glucose. So it would be what, 12 times 6 plus 12 plus 16 times 6. Is that what it is? My apologies here. And I believe that's 180. So that's where the 180 comes from. We're talking about glucose here. To 1 mole, because we have to convert those to moles. We're going to multiply by our 280. Those are kilojoules. And we only have 1 mole, so that's not going to be a problem. That's not going to be a problem. So we have 9.22 divided by 180. That turns us into moles. Multiplied by our there we go. So we have negative 143 sig figs. It looks like we should stay with 140. We should stay with 3 sig figs. And always remember your units. Alright.